You know that feeling, right? You're trying to get a quick, um, accurate answer from a search engine, but it's something real-time, maybe something, well, dynamic.
Hmm.
Maybe you're checking specific concert ticket availability for next Tuesday, or current inventory for some gadget at a local store.
Yeah, things that change constantly.
Exactly. And you hit search, and often what you get back is just like a wall of static text or something frustratingly out of date. I once spent, I swear, half an hour trying to figure out if a local restaurant had outdoor seating right then on a busy Friday night.
And what did you get? Old menus.
Pretty much static menu pages. It felt like I was trying to, I don't know, read tea leaves.
It's a classic problem. It really is.
Yeah.
It's like asking a brilliant historian for today's stock price. They
Mhm.
might hand you a beautifully preserved newspaper from last week.
Right. The information exists somewhere.
It does, but it's just not accessible in a dynamic way. It doesn't reflect the present moment.
That's a really crucial distinction.
Mm-hmm.
So today, we're taking a deep dive into, well, an exciting new frontier in AI search. We're exploring a breakthrough called TURA. That's the Tool Augmented Unified Retrieval Agent.
TURA. Okay.
Our mission here is to kind of uncover how AI search is evolving beyond just, sifting through static web pages.
Mm-hmm.
We're talking about AI that can actively interact with dynamic, real-time information sources.
Which could essentially transform how you get informed, how you make decisions online.
Exactly. We're going to look at the engineering brilliance behind it, and importantly, its very real-world impact.
This is a massive leap forward, really. Think of it as moving from just passively reading a book to actively, well, conversing with the living world, digitally speaking.
Okay, so let's set the stage. To really appreciate where TRA is taking us, we should probably look at where we've been. For decades, traditional search gave us those 10 blue links, right? A list of static web pages.
Classic search results page, yeah.
Then, with large language models, LLMs, we saw a shift to conversational AI search. That primarily used something called retrieval augmented generation, or RA.
Right, a RAG. And RAG was a significant step, no doubt. It basically allowed LLMs to read up on a topic from a huge digital library like the web, and then formulate an answer that was grounded in that information.
So it's great for summarizing existing stuff, historical information that's already written down.
Exactly. Powerful for that.
But here's the catch, the Achilles heel of RAG, you could say.
Mm-hmm.
It's built for static content. It's fantastic at summarizing what's already been indexed and stored.
Mm.
But what if the information you need isn't just sitting nicely on a web page? What if it's, well, dynamic?
Precisely. That's where our RAG really struggles. Time-sensitive queries are a huge problem for it. For instance, if you ask about high-speed train availability from Beijing to Shanghai for a specific date next month,
Okay.
a traditional RAG system can only pull info from static web pages. It might tell you about typical schedules or link you to booking sites.
But it can't actually check the live system.
No. It can't interact with a live booking system to confirm exact seat availability or real-time prices. It's essentially blind to the present.
Or like checking current stock levels for a product at a specific store.
Yeah, that information isn't on a web page in the static sense.
It needs to be generated, right? Through an active interaction with, say, an API or a database.
Exactly. And that's where I just hits a wall.
And, this isn't a totally new challenge. People have tried to tackle this before.
Right. Earlier attempts, you had things like Google's OneBox or Baidu's own Aladdin system. They tried to bridge this gap, but the issue was they relied on these brittle, handcrafted integrations.
Meaning they were hard to scale.
Incredibly difficult to scale, yeah. Each new dynamic data source, each API needed its own custom-built solution.
Which sounds like a nightmare for complex queries, things with multiple parts.
Absolutely. Multifaceted queries were almost impossible to handle flexibly.
Okay, so we've got the problem. RE is great for the past, but blind to the present, and older solutions didn't scale. This is where Baidu Inc. steps in with TURA.
The Tool Augmented Unified Retrieval Agent.
Yes. They introduced it as this novel, three-stage agentic framework, designed specifically to systematically connect that static ARG world with dynamic information sources.
And what's really fascinating here, I think, is the fundamental shift. They call it an agentic shift.
Agentic meaning?
Meaning TRA moves beyond just passive document retrieval, simply reading what's already there, to active real-time data acquisition. It basically enhances LLMs with the ability to use external tools.
So it's like giving the LLM hands and feet, not just eyes.
That's a great analogy. It can do things now, pull live data, interact with services, perform actions out in the digital world.
And this isn't just a research paper, right? You
Yeah.
mentioned real-world impact.
Not at all theoretical. TURA has been fully deployed since May 2025. It's already successfully serving tens of millions of users right now. It's proving its viability and effectiveness today in a world-class AI search product. This is happening.
Okay, so how does it actually do that? How does TURA manage to interact with the live internet so effectively?
Well, it all comes down to its quite brilliant three-stage engine. Let's unpack stage one first. Intent-aware retrieval. This is about truly understanding what you, the user, actually need.
Right, because queries are often messy. They can be underspecified or have multiple parts, like that example earlier. Beijing trip, June 10-15, need hotel, 2-3 attractions, and things to do.
Exactly. That's a lot packed into one sentence.
Mm-hmm.
A traditional system might just get confused or only handle part of it.
So how does TURA deal with that complexity?
It uses an LLM, but configured specifically as a query decomposer. It's like LLM magic for breaking things down. It deconstructs that complex query into separate atomic subqueries,
Atomic meaning.
meaning single manageable requests. So that Beijing trip query becomes things like search Beijing weather, June 10-15, find top attractions in Beijing, hotel booking options, Beijing, June 10-15, maybe even plan a route for Beijing attractions.
Okay, breaking one big problem into smaller, solvable ones.
Precisely. That decomposition is absolutely critical for tackling complex problems efficiently.
But, all right, once it has these specific subqueries, how does it know which tools or services out there can actually answer them?
Good question. This brings us to bridging what they call the lexical gap. Basically, the gap between how a user asks a question and how an API is described.
So how does it bridge that gap?
TURA does something clever offline before you even type your query. It generates a large, diverse set of synthetic queries for each available tool. Baidu calls these tools MCP servers. Think of them as specialized microservices or APIs that handle specific real-time tasks, checking flights, product inventory, weather, etc.
So it's like brainstorming all the ways someone might ask for that tool's function.
Exactly. It creates what they call an augmented document for each tool. TURA is essentially teaching itself what each tool does by imagining all the ways a user might ask to use it. This gives it a much deeper semantic understanding of the tool's capability, way beyond just reading a formal API description.
That makes sense. Is there an optimal number of these synthetic queries?
They found a sweet spot, actually. Around 20 synthetic queries per server seems to provide good semantic coverage without adding too much noise.
Okay, so it's pre-learned what each tool does. Now a subquery comes in.
Right. When a subquery arrives, TURA uses a dense vector retrieval approach. Think of it as a smart matching system. It doesn't just look for keywords. It understands the meaning or intent of your subquery.
And matches it to the best tool.
Yes, semantically matches it to the most relevant MCP servers. It's like connecting you with the right specialist for your specific problem, even if you didn't use the exact technical terms. It even aggregates scores across multiple subqueries for complex requests to make sure it's picking the best set of tools for the overall job.
Okay, that's stage one. Understand the intent, break it down, find the right tools. What's stage two?
Stage two is the DAG-based task planner. You can think of it as the master strategist.
DAG.
Directed acyclic graph. It sounds technical, but the concept is intuitive. For simple queries, TURA might just execute the tool directly. But for complex ones involving multiple steps or tools, it needs a plan.
And it doesn't just do things one after another?
Not necessarily. This is where the power of parallelism comes in, thanks to the DAG.
Like that recipe analogy you mentioned earlier.
Exactly like that.
Yeah.
Imagine the DAG as a flowchart for your query. It maps out the subtasks and, crucially, their data dependencies.
Dependencies meaning which tasks need results from other tasks before they can run.
Precisely. Let's go back to our Beijing trip example.
Okay.
The task for planning a route, the path planner, depends on knowing where the hotel is booked and which attractions were chosen. It needs that data first.
Right. You can't plan the route without the destinations.
But searching for the weather in Beijing, that doesn't depend on anything else in that query.
So it can run that search immediately, in parallel.
Yes. It can happen simultaneously while TURA is maybe finding hotels or suggesting attractions.
So the DAG figures out what can run at the same time.
Correct. It allows for optimal parallel execution.
And the payoff is speed.
A huge payoff in speed, especially for those complex multi-hop queries. The results showed a 44.2% reduction in latency for these complex cases.
Wow, nearly halving the wait time.
without sacrificing the success rate. It's like having multiple intelligent agents working efficiently on different parts of your request all at once.
Okay, makes sense. Faster execution through smart planning. Now, stage 3.
Stage 3, the distilled agent executor. This is where speed and accuracy really combine in an interesting way.
So you might be wondering, why not just use one of those huge, super powerful LLMs like, say, DeepSeek V3 for every single little tool call? They're
Real
smart.
point, right?
They are incredibly smart, but the simple answer is real-time performance. It comes down to latency. Too slow.
Potentially, yes. Directly using a massive LLM for every fine-grained decision within a complex task. Well, it would likely be too slow in a live production system. Think about all the context it might need to process for each step. The conversation history, descriptions of dozens of possible tools or APIs, the current state of the task.
That sounds like a lot for the model to chew on for every little action.
It is. It could lead to unacceptable inference latency, meaning you'd be waiting too long for the answer.
So TRA uses a different approach.
A very clever one called agent distillation. They frame it as a train with thought, infer without thought paradigm.
Train with thought, infer without thought. Okay, break that down.
Sure. First, they take a powerful teacher model, like DeepSeek V3 you mentioned. This teacher model generates expert demonstrations of how to use the tools. Crucially, these demonstrations include its detailed chain of thought reasoning.
So it's like the master chef explaining why they're adding the salt now, why they're whisking this way.
Exactly. It shows its work, the reasoning steps, and the final action, like calling a specific API with certain parameters.
Okay, so you get these detailed examples from the big model. Then what?
Then, this raw data, these demonstrations, are rigorously curated. They're checked for correctness and efficiency. Basically, quality control.
Makes sense. Get rid of any bad examples.
Right. And then a much smaller student model, they use Qwen34B in the deployment, is fine-tuned specifically on this high-quality, thought-rich data generated by the teacher.
So the small model learns from the best examples provided by the big model, including its reasoning.
Precisely. But here's the really interesting part, the infer without thought bit.
Okay.
During inference, when TURA is actually live and answering your query, the smaller, fine-tuned student model is instructed to only generate the final action. It skips outputting the explicit chain of thought steps.
Wait, it skips the thought process.
Yeah.
How does it know what to do accurately then?
Because it has implicitly learned the reasoning during that specialized fine-tuning phase, the thinking is baked in, even if it doesn't spell it out anymore.
Whoa. Okay, that's counterintuitive, but really cool. What's the result of that?
The results are genuinely astounding. The smaller Qwen34B distilled model actually achieved an 88.3% tool calling accuracy.
Okay. How does that compare?
Get this. It surpassed the teacher model, DeepSeek V3, which was at 82.4%, and it even beat GPT-4o, which scored 81.7% on the same benchmark.
Hold on. The smaller distilled model was more accurate at calling tools than the giant teacher model and GPT-4o.
That's what the results show.
That completely flips the script on bigger is always better, doesn't it?
It certainly challenges that assumption for specific, well-defined tasks like tool calling.
And the speed. What about the latency?
That's the other kicker. It reduced the P80 latency, meaning 80% of calls were faster than this by a staggering 66%.
56%.
Yeah, down from about 2,200 milliseconds for the non-distilled 4B model to just 750 milliseconds for the distilled version.
So significantly faster and more accurate. That's incredible.
It really is. It points towards a future where highly specialized distilled models might be the key for efficient, real-world AI applications.
Which makes sense why they chose it for deployments.
Absolutely. Baidu went with the Qwen34B distilled model because it hit that sweet spot. Superior accuracy combined with cost-effectiveness. It can run efficiently on a single GPU.
A very pragmatic, but also groundbreaking choice.
Definitely.
Okay, so the engineering sounds incredibly impressive. 3 stages. Understanding intent, planning with parallelism, and fast, accurate execution via distillation. But how did this translate into actual user experience? What about the validation?
They did extensive testing, both offline benchmarks and live A/B testing in production.
Let's start with offline. How did TRA stack up against, say, standard RAG?
Significantly better. In human evaluations on accuracy, TRA scored 87.5% compared to RAG's 65.3%.
That's a big jump.
Huge. Maybe even more importantly, in faithfulness, which means the answer is actually grounded in and consistent with the information from the tools it used.
Right. Is it making stuff up or sticking to the facts it found?
Exactly. TRA hit 96.2% faithfulness, whereas RAG was down at 72.4%.
Okay, so TRA is not only giving more accurate answers, but it's also much more reliable in basing those answers on the actual data it retrieves from tools.
Correct. It's providing correct and grounded answers directly from the source.
That's offline. What happened when they put it live, head-to-head with the existing system?
The live A/B testing results were also really compelling. In the actual production environment, with real users, TURA increased the overall session success rate by 8.9%.
Nearly 9% improvement in users successfully getting what they wanted. That's substantial.
Very substantial. And it showed an 8.7% overall performance advantage in direct comparisons. Users rated the TURA results as good, meaning strictly better than the baseline system, in 13% of cases.
And did it reduce bad experiences?
Yes, it significantly reduced bad ratings down to only 4%. So better success, better ratings, fewer bad experiences.
Were there specific types of queries where it really shone?
Absolutely. The researchers highlighted scenarios needing that real-time data accuracy. Things like getting precise, up-to-the-minute train schedules or accurate current weather forecasts.
The kind of stuff RA struggles with.
Exactly. Where traditional RE systems often produce significant discrepancies, sometimes just giving outdated info or completely wrong times. TURA provided highly accurate live information pulled directly from the authoritative sources via the tools.
That led to fewer problems overall.
Yes, they measured a reduction in total issues reported by users by a remarkable 16.7%.
Okay, the validation seems pretty clear, both offline and live. It works, and users notice the difference. So let's bring this back to the person listening. What does QRA mean for you, the learner, the person just trying to get things done online?
Well, firstly, I think TURA serves as a kind of blueprint for the next generation of conversational AI. It fundamentally allows you to get precise, real-time answers for types of questions that were, frankly, impossible or very frustrating for conventional systems before.
Yeah, those dynamic, need-it-now queries.
And it really acts as a shortcut to being well-informed. This system is designed to ensure that when you ask a question, particularly one needing live data or complex interactions,
Like booking travel or checking inventory.
right, you get not just an answer, but an answer that is accurate, that's up to date, and that's based on high-fidelity information pulled directly from authoritative sources.
And quickly, based on that distilled executor stage.
Exactly. Delivered with remarkable speed right back to you.
You know, thinking about it, TURA really seems to represent a profound shift, doesn't it? We're moving beyond simply finding information.
Towards actively interacting with the digital world through AI.
Yeah, it's like your search engine isn't just a librarian anymore. Now it's also your travel agent, maybe your stockbroker, your inventory manager.
All rolled into one, potentially, capable of doing things based on your request.
Exactly, that shift from passively searching to actively interacting. It just opens up so many possibilities.
It really does.
So maybe a final thought to leave folks with. What does this TURA approach really mean for our future interactions with technology? Are we heading towards a point where we stop searching in the traditional sense?
And it's dead.
We just converse. Converse with an intelligent agent that handles, well, everything from booking complex trips to managing daily tasks.
An agent that seamlessly pulls information and performs actions across countless dynamic sources behind the scenes.
Yeah. What new possibilities does that open up for how we learn, how we acquire knowledge, how we engage with services online? Especially when the AI can actually do things on your behalf, not just tell you about them. What comes next?